Statement of our question is, this is very important type. If G is some group, so it is a group of order p raised to power n. So what is p? It is a prime number. And H is a proper subgroup of group G. Then we have some element A belongs to G, but A does not belongs to H, such that it satisfies this property. Now, to prove this result, now in the given part, what is the order of group? So this is a p raised to power n. This is p raised to power n. Now we shall prove it with the help of induction. So first I take n is equal to 1. To prove this result, I take n equal to 1. So it implies order of G which is equal to P. Order of G which is equal to P. Since H is not equal to G and H is subgroup of G, so by Lagrangian theorem, order of H divide order of G. So what is order of G? Order of G is equal to P. Then order of H has two possibilities. Either it is 1 or P, because P is prime number. Now since order of H and order of G are not equal, then it implies order of H is equal to 1. Why? What is the reason? The reason is H is not equal to G. So that's why order of H equal to identity. Then it means H consisting only one element, so which is called a identity element. Now if I take some A element belongs to G, so which is different from H, so it is a non-identity element. So I write it as A H A inverse, yeah, A into H into A inverse. What is this? Since H is identity, so it will become A into A inverse. So what it becomes? It becomes only identity. So what it becomes? It becomes H. So it satisfies our result when order of H, order of G is equal to P. It means the result is true for n equal to 1. Now, assume that result is true for all group of order, all groups of order less than order of G, because we are doing with the help of induction. So first of all, we prove it for n equal to 1, then for all group of order less than order of G, right? Now suppose H is equal to normalizer of H. Suppose that H is equal to normalizer of H. So it means normalizer of H means, what is the normalizer of H? Which consisting HA is equal to AH. So suppose H is equal to normalizer of H. So I take this assumption. Now since center of G which is a part of normalizer of H, as we know that. And normalizer of H we taken here is equal to H, and also we know that H is a part of G, but it is not equal to G. It means H is proper subgroup of G. If H is proper subgroup of G, then Z of G is again proper subgroup of G. So it implies H by ZG. This is center of G. So since H is proper subgroup of G, so this is a proper subgroup of group G by center of G. So what is the logic behind it? Since the center of G is a proper subgroup of G, that's why H by center of G is proper subgroup of Z by center of G by center of G. Also, order of G by center of G, this can be written as order of G and order of center of G. This can be written in this way. Now, the given group is a group of order p raised to power n. Then the previous result show that order of center of G is always greater than 1. If it is always greater than 1, so it means this is less than order of G, right? Now it means by the given assumption, our result is true for all groups of order of G. Now here I get this is a proper subgroup H by center of G. So in the assumption H, and it is a proper subgroup of G by Z of G, and the result is true for this. So it means our result is applicable to this values. Then it means we can find a sum. So there exists a sum element which belongs to G by ZG, but which does not belongs to H by ZG. So if I put center of G is as a, for simplification, is equal to n, then it means I have some element belongs to this which does not belongs to this and satisfied our condition. So it means there exists some element Na which belongs to G by n, and n by Na which does not belongs to H by n. Also this element, this satisfy our given condition. What is the given condition? That is this element Na into H by n into Na inverse. So Na inverse which is equal to H by n. So that is by given assumption, we have given result. So by given result, we satisfy this values. So I write for simplifications. So center of G is equal to this values. Now this means this element, any element from this is belongs to H by n for some element. So it means, what it means? It means if I take some element from H by n, so it means Na into n small h into Na inverse, this element, it belongs to, this product belongs to H by N as small h belongs to capital N. Why this is? Because this value, this set is equal to this set, and the element of this set is of this kind. So it means if this set is equal to this values, so this element belongs to this set. So it implies, by taking the product property of right coset, so this will become N A H A inverse. This belongs to H by N. This belongs to quotient group H by N. From this, it means this element belongs to H. So remember that. So if N into this belongs to quotient group, if element of this belongs to quotient group, so A H A inverse, it belongs to capital H. It belongs to capital H, as H small h belongs to again capital H. So it means this element is of this kind, A inverse, which is equal to small h1, and where small h1 which belongs to capital H. So A H A inverse, this belongs to this values, and this value is equal to H1. So this value H1 belongs to H. Also, I can say that this set, this is a H into A inverse. This is a subset of capital H, because this element is equal to this, and this H1 belongs to capital H. So I here directly taken as this element is a subset of this value. Also, we know that order of A H A inverse, this is equal to order of H. So that by previous result, we know that this condition is satisfied. It is a subgroup of H. Also, they have same order. If they have same order, then both the set will be equal. AH A inverse, which is equal to H. So it satisfies this condition. So AH A inverse, which belongs to this values, which is equal to H. So what we get from this, it means AH A H is equal to HA. It implies A belongs to normalizer of H. So from this I get this belongs to normalizer of H. If it belongs to normalizer of H, so which is equal to, I taken it as H. So it implies normalizer of H as NA belongs to H by N, as in the given part as NA. This NA, this is belongs to, does not belongs to H by N. So this is why we choose that this NA does not belongs to H by N. So if NA belongs to H by N, so it means this A does not belongs to H. This A does not belongs to H. But here A belongs to H. So which is a contradiction. So here what we get, this A, it implies this A does not belongs to H. This does not belongs to H. But A belongs to here. A belongs to NH. A does not belongs to H. So what we get? We get H is proper subset of normalizer of H, because we find a some element which belongs to NH, but it does not belongs to H. So I find H is a proper subset of these values. If we find it is a proper subset of these values, so which contradict our result, so which prove our result. So the second statement of this result is also in a finite P group G. So what is in a finite P group G, in a finite P group G, every proper subgroup of a group is a subgroup is a proper subgroup of its normalizer in G. Normalizer in G. So this is the second statement of this group. So what we get, H was a proper subgroup of a group G, and we prove that it is also a proper subgroup of normalizer of H. So H is again proper subgroup of its normalizer of H. Now next result is G is some finite group in the given part and H is normal in G. So GCD of order of H and order of G by H is equal to 1. Then show that H is a unique subgroup of a given order. Now to prove it here, it is a uniqueness. So what is the, I take order of H is equal to M and order of G over order of H is equal to N. So here it means order of G is equal to M into N, where GCD of Mn is equal to 1. So that is my given part. Now to prove that H is a unique group of order M. Now H is given, which is a normal in G. So I take some another subgroup such that order of H and order of that group are same. So I take, to prove the uniqueness, let K be subgroup of group G such that order of H and order of K, they are same. Since its order is M, so this means its order is M. So that is to prove the uniqueness. So I will prove the uniqueness of H by proving that H is equal to K. Now, since H is normal in G, so this is a normal subgroup in G, then it implies HK is equal to KH. So it means HK is a subgroup of group G by using the previous result. So it means H is a subgroup of the group G. If HK is a subgroup of the group G, then by Lagrangian theorem, so you write here by Lagrange's theorem, order of HK, it divides order of G. So here write by Lagrangian theorem. So here write the name of the theorem that we used by Lagrange's theorem. So order of HK which divide order of G. So in the given part, what is order of HK? Order of HK is written as order of HK can be written as order of H order of K and over order of H intersection K. So if we know the value of order of H, that is M, what is order of K, that is again M. So I take its order as D. So as order of H intersection K is equal to D. So I take this is equal to D. So it means when we substitute its value at this place, so it means M into M by D. So it implies M into M by D which divides order of G. So what is order of G? Which is M into N. So we know that M into N. So it implies M over D divide N because it is common part. M is common part. So M of D, it divides these values. So it implies if we multiply by N D, so D into M over D again divide N into D. So it implies this M divide ND. So I get M divide ND ja DN. So in the given part, the GCD of M and N is equal to 1. So what we get, since M divide ND and GCD of M and N is equal to 1. So by using the result from number theory, it implies M divide D. So we get M divide D, right? So what is H intersection K? So as H intersection K, it is a part of H as well as K. So this is a subgroup of group H again by Lagrange's theorem. So order of H intersection K, it divide order of H. So what it means? It means D divide M. Now from this result, M divide D and D divide M. So it means both are equal. So it implies M and D are equal. So what it means? It means H intersection K is subgroup of H and both have same order, H intersection K, which is equal to order of H. So this is possible when H intersection K is equal to H, and this is possible when H is equal to K. So which prove the uniqueness of this group. So in this way we can prove that the uniqueness of this result.